to this latest edition of Space Connects Us. I'm Stuart Clark, and for the next hour, I'll be your host as we talk about potentially hazardous asteroids and how astronomers calculate the chances that a particular asteroid might strike our planet. Now, we're going to hear about the fascinating sequence of events that the astronomers go through and what missions and telescopes and missions they use to make their calculations. Now, as of this morning, there are 1,338 near-Earth asteroids on ESA's risk list. This is a catalogue of all objects for which there is a non-zero impact probability that's been computed. Now, I want to stress very clearly that this does not mean that those asteroids will hit the Earth. All it means is that with our current observations, we cannot yet rule out an impact in the next century or so. So to tell me how the world's leading space agencies go about ruling out such potential asteroid strikes, I'm joined today by two absolutely fascinating individuals. Marco Micheli from ESA's Near-Earth Object Coordination Center in Frascati, Italy, and Steve Chesley from NASA's Jet Propulsion Laboratory, Pasadena, California. Marco, Steve, welcome to Space Connects Us.
Thank you. Thank you.
Now, before we jump in with the technicalities, I'd love for our audiences to get to know you both a little better. So I wonder if you could start by telling us how you came to be studying asteroid orbits. And Marco, I believe that you were an amateur astronomer as a child.
Yes, exactly. I started as an amateur astronomer when I was a kid, and during elementary school, I was really fascinated by the sky in general. Then I joined the local amateur astronomers community in my hometown. And when I was in high school, I discovered that some of them were actually studying these things called asteroids. And I was immediately really fascinated by them. And I mean, if you had asked me when I was 14, what do you want to do as an adult, as you're living, I would have said I want to study near-Earth asteroids. So I was really hooked into this since a very young age. Then, of course, I turned this passion, this hobby, into a profession with my degrees first and then with my current job. It was really an adventure that is still going on, and I love it.
Yeah, you totally meant to be here doing this job. If it captured, near-Earth asteroids captured you so early. Steve, you came a slightly different route, I believe, as you were an Air Force pilot and studied engineering.
That's right. Yeah, I have a much more indirect route to asteroids than Marco does. After university, I went to the Air Force. I was a pilot flying B-52s. I got out as soon as I could. I went to grad school to study more engineering, and eventually, in the late 90s, I landed at the University of Pisa in Italy, working with the late Andrea Milani, where we built the first asteroid impact monitoring system. Then around 2000, I sort of imported that technology to the United States, and we built a companion system here at the Jet Propulsion Laboratory for NASA.
Absolutely fascinating. Well, you are so welcome here today, and we are extremely grateful that you could join us and just share what you do, because as I said at the beginning, this is truly fascinating stuff. Now, a word to our viewers before we really jump in, and that is, if you have any questions, and I'm sure you're going to have a lot because this is a great topic, please type them into the chat wherever you're viewing, whether that's YouTube, Twitch, or Facebook. And we've got moderators that will sift those through and pass them to me so that I can ask our guests. I'll get through as many of those questions as I can towards the end of the hour. But first of all, I've got my questions to ask you both. So Marco, I'm sure that there are a number of viewers that are aware that there are telescopes around the world that search the sky night after night looking for asteroids. Now, how do we know when those telescopes have found an asteroid?
Well, these telescopes are dedicated mostly to do this. So they just scan the sky, the night sky, every single clear night they have. And they do it by taking images of the sky. Nowadays, all the professional telescopes are operated with cameras. So there's no astronomer actually looking through the telescope. It's just cameras. So they shoot pictures at the sky, at different areas of the sky. not just one picture, but actually more than one, typically 4 or 5 pictures separated by a few minutes from each other. And asteroids, in a single image, they look like a star, but contrary to the stars, they move. So what they do is they compare the sequence of 4 or 5 images distributed maybe over an hour, and they look for any little dot, any little point that moves through the star fields. If they see something that moves, that's an asteroid. And then they have to check if it's a known one or not, and if it's close or not. And that's a slightly different story. But yeah, at the moment, when I say they, it's actually, today it's mostly machines, of course, it's not human beings. But it's also interesting the fact that human beings are still really good at this. And in the end, in most cases, any new asteroid that is found by these projects, by these automated telescopes, is actually still validated by a human eye. So there are astronomers who look at what these telescopes and computers have found, and they say, okay, this is a believable asteroid. This is really an asteroid that moves. So I'm going to notify the rest of the planet that there is something new right there that is worth checking more carefully.
And this detection part of it, this is just the beginning, isn't it? Because yes, it's a different thing to then calculate an asteroid's orbit. So I think we're going to talk quite a lot about the details of doing this this evening. But give me the broad brush approach of how you go about the process of calculating an asteroid's orbit.
Well, I'm going to say my half of the story, and then Steve maybe can complete with his own half. The side that I do, which is the observational part, I'm an astronomer, is taking these observations, measuring the position of the asteroid in the sky. And well, the first time it's seen, of course, these positions are notified to the world. And if the object seems to be interesting, we start this very interesting and fascinating inter-exchange between astronomers and mathematicians like Steve, that we do the observations, they use it to compute a sort of preliminary orbit of the asteroid that then we use to observe the asteroid again and get more data that we can give them to get an even better orbit of the asteroid. And this back and forth goes on for as long as it's needed to clarify that a particular asteroid is relevant or not. So it's always an exchange between we observers observing with telescopes in the sky, and then the mathematical counterpart of us doing the computational work behind the hood that tells us what we have to do next, where we have to point the telescope next. And so it's a very fascinating exchange of information that happens in basically near real time on very short time scales, and allow us to complement each other. And then Steve can say more maybe about his side on what exactly they do with the data we send them.
Yeah, Steve, let's bring you in. Let's bring you in there. So Marco takes the observations, sends you the data. What do you then do?
Yeah, I agree with Marco. This is sometimes a very intense collaboration when we have something that we're really urgently trying to understand what kind of an object, or what kind of an orbit, I should say, these objects are. There's a lot of back and forth between those who are producing the observations that are required in order to understand the orbit of the object. What we do is we take these measurements, essentially, basically, where on the sky is it at a series of times when the images were taken, and we say, let's suppose it's this orbit. We make an initial guess at the orbit, and we see if that initial orbit matches the observations. And of course, it's just a guess. It's not going to match those observations. So we have to start tuning the orbit until it exactly falls on those observations that come in, or as close as possible. Of course, if you have a lot of observations over a few nights, then you're not going to match everything exactly, because all the measurements have some measurement noise associated with them. So we try and minimize what looks like noise in the orbit fit. And then sometimes within just a few hours, we can recognize that something's very interesting. And of course, the observers are notified right away and through automatic channels. In many cases, though, this will go through a sort of a more mundane process where the data will accumulate over a period of days and weeks, and we'll understand much better as time passes exactly what kind of orbit we're dealing with.
Now, we're going to talk more later on about the follow-up observations and how you decide which asteroids to follow up and the urgency with which you need to do that. But right just at this moment, Steve, I'd like it if we could just back up a tiny bit. And we tend to talk about asteroids as this big general group of objects, but not every asteroid is a threat to us, is it?
No, certainly not. The vast majority of asteroids, of course, reside in the main belt between Mars and Jupiter, right? We have over 1 million asteroids that we know about out there. There's about 24,000 or 28,000 asteroids that are what we say in the inner solar system, which are kind of well inside of Mars's orbit at some point in their orbit. And so these are the near Earth objects that we're mostly interested in. And of course, among those near Earth objects, 28,000, there's only a few thousand that are particularly interesting for some possibility of future encounters or even impacts with the Earth. So it's safe to say that most asteroids are not interesting from the perspective of Earth hazard, and yet the ones that are, of course, are the subject of a lot of scrutiny.
And of these 1,000 or a couple of thousand that are sort of interest for the potential they have to impact the planet, are these what we would call potentially hazardous asteroids? Is that the definition for them, or is it slightly different?
Well, we've got a lot of jargon in our business, just like any other technical field, right? So potentially hazardous asteroids, maybe first I should back up and talk about the astronomical unit, which is our standard yardstick for measuring distances in the inner solar system. The astronomical unit is essentially the distance between the Earth and the Sun. It's about 150 million kilometers, 93 million miles, if you're still into that kind of thing. And so any asteroid that could possibly come within 0.05 astronomical units of the Earth is considered a potentially hazardous asteroid if it's also large. And large here is about 140 meters. So if it's large enough to really be potentially dramatically destructive, and it has a possibility of coming fairly close to the Earth. 0.05 AU is not that close by our standards. But anyway, that's the set of objects that bear special monitoring, and we do. There's another class of objects that we know has an actual possibility of impact, and we call those VIs, which is another bit of jargon for virtual impactors. And those virtual impactors, there's about 13 or 1,400, I think, that we're monitoring right now. Many are very small and of not much concern for hazard, and many of these small ones we haven't seen for a very long time. But those are the ones that might hit the Earth, and they're the ones that we pay extra special attention to, and we try and get more data so we can better understand their future pathways and understand if the Earth really is or is not threatened by them.
And of these sort of 13 or 1,400 of these VIs, these virtual impactors, Marco, I'm assuming that those are the ones that ESA maintains on its risk list that I mentioned at the beginning of this. And a question for both of you, we'll start with Marco and then go back over to Steve, is how often do new asteroids go on to the risk list, and how often do old ones come off it? I noticed when I started researching for today's stream at the beginning of the week that there were 1,339 objects on ESA's risk list, and today when I checked it was 1,338, so we're one safer than we were at the beginning of the week. So talk me through the process from both your points of view, Marco first, about when they go on and when they come off.
Okay, so interesting question. The numbers you've seen, the fact that there is variation of order of a few units after a few days, is kind of typical. I would say that on average, there's maybe one or two that go on and one or two that go off every day, and so kind of keeps the overall total more or less balanced. It's a dynamical process, so it's not a very stable list, as I just said. It changes every day. There are some new entries or new objects leaving it basically almost daily. in terms of how this actually works, well, every time the going in is simply when an object is discovered, the first time it's announced, it gets processed by these systems, the one we have in ESA and the one that Steve has at NASA JPL. And if they see a possible impact in the future, they get added to the list with some information on the time of the impact and so on, and the probability and the energy and so on. That's what feeds our observing list, our target list of us as observers who try to observe them again with our telescopes. And our observations are then typically what leads to the removal of these objects from the list, because as soon as our observations are processed by, again, the orbit computers, by the orbit calculator, they clarify the orbit, they improve our knowledge of the orbit enough that now we see that that particular possible impact in the future is not possible anymore. It is not compatible with the new data anymore. And therefore that object leaves the list. Sometimes maybe the whole object doesn't leave the list because there are some of these asteroids that have multiple possible future times of impact. So maybe the new observations clarify that two of the possible dates do not correspond to an impact, but maybe the third one remains. And so we have to get more data over the next few days and weeks to, again, proceed in this cycle. And then, of course, hopefully in the end, clear all possible dates and just remove the object from the list. And this whole process, it's typically, we are typically handling a few objects in and out every day with this mechanism.
Fascinating. Yeah. And Steve, over at JPL, is your list the same as ESA's, or do you independently maintain the list so that you can cross-correlate?
Ours is fully independent. That's one of the big objectives of having multiple systems between to monitor for these. We don't want just one system to miss something. So whenever we have something particularly interesting, our systems automatically send emails to the other teams to say, hey, look, this is an interesting case. Let's get together and make sure that we all agree and have the same answer, which is very often the case. And we do have different lists. Ours at the moment is 1,377 entries, which is a little different from ESA. It's a kind of normal discrepancies because some of these objects, how do I say, it's sort of a statistical look at what's going on with the object. And for very low impact probabilities, we may find something or we may not find something. It's almost like a coin toss. For higher impact probabilities, say above 1 in a million, we always have the same sets and we always agree. And so there's no discrepancies, but just the way these systems are designed and the way they work, for cases where we find something with a very low impact probability, it's sort of random as to whether the other system will have it also. I will add, just echoing what Marco said, these things come in, they come out. A great many new discoveries, say with only 2 or 3 nights of data, 100 years in the future, they could be almost anywhere along their orbit. Sometimes their uncertainties can wrap multiple times around the orbit in 100 years. What this means is early on in the discovery process and the tracking process, there's likely to be an impact possibility with very low likelihood because there's such a huge uncertainty space that the asteroid is occupying. So very often something will come on with 3 days of data, then it'll get more attention because of that, and it'll be taken down because they got enough data to rule out those impacts. It's a very routine process to say, hey, here's a possibility. It's a 1 chance in 10 million of an impact in 40 years. The astronomers get their telescopes. Marco is one of the leaders in this arena, and they go get more data of very high precision. And we feed it back into these systems, and they say, okay, never mind, this one's good now. We can take it off the list. That's the process. It works well. It's been working well for a couple decades now.
It was very interesting to me as a science journalist as well, that if you go back, say, 15, 20 years or so, there was a flurry of headlines about these sort of potential impacting objects. And then And then the better we got at detecting asteroids, the less journalists could keep up with all the headlines of potentially impacting asteroids. And now we understand, this is why it happens, because of the process that you have to go through.
Right, and there was always in the early days, as you mentioned, there was always the first headline was astronomers predict Earth impact, which is already not true because we just said there's a possibility, not a prediction. And then the next day, the headline reads, "False alarm: astronomers made mistake." But that's just as wrong as the first one, right? It's like saying that if somebody says a hurricane might hit Alabama, well, it might, but if it doesn't, that doesn't mean that their initial prediction was actually wrong. It was a possibility that they articulated, and if it went somewhere else, that was also part of their prediction.
Mm. Now, Steve, I believe that when we're calculating asteroid orbits, it's not as straightforward as it sounds, because initially we think, we're very used to the planets moving in their orbits, and they're never really deviating very much from those orbits. But the asteroids, they're an evolving orbital population, and they can change, even very slightly sometimes, their orbits. And I believe one of your expertise is in doing those kinds of predictions of these little perturbations that happens to these asteroid orbits, things like the Yarkovsky effect, for example. I wonder if you could just talk us through the kind of things that complicate these orbital calculations for asteroids and how you go about modeling these things.
Sure, that's a great question. How much time do we have? So I should back up and emphasize, you're right, that the orbit of the Earth, the orbit of Mars, they're pretty much what they are, and they're going to stay what they are. They have been and they will be. Asteroids are quite different. We know that asteroids originated, these near-Earth asteroids originated in the main asteroid belt out beyond Mars, and they migrated inwards primarily from the influence of Jupiter in most cases, and Jupiter kind of nudges them into the inner solar system. And once they get into the inner solar system, they can start to have close approaches to the terrestrial planets, in particular Mars and Earth, and sometimes Venus. So when they have a close approach to, say, Earth, that can dramatically change the orbit and completely disconnect it from the main asteroid belt. So now you have an asteroid that's circulating in the space of Earth, but its orbit's generally not going to be a lot like Earth. It might be much more elliptic or inclined relative to Earth. So now we have a near-Earth asteroid, and we're trying to monitor where it's going. And all kinds of very subtle things start to come into play when you're trying to be as precise as you can in order to, say, do an impact hazard assessment. First of all, besides all the planets in the solar system that are perturbing this asteroid, we're currently using dozens or even hundreds of main belt asteroids, large main belt asteroids that can have a detectable effect on some of these trajectories. So these are very small effects, and yet they're significant for us. And you mentioned the Yarkovsky effect, which I spent a lot of time working on this and understanding it. This is the effect where if sunlight heats an asteroid on the daytime side, and then the asteroid rotates and it radiates that heat into the afternoon and evening direction. And so that heat is coming off asymmetrically, more on the evening side than on the morning side. That provides a thrust. We call it photon thrust. The photons carry momentum, and they actually push the asteroid either inward towards the sun or outwards towards the sun very, very slowly over millions of years. In the inner solar system, though, that also pushes them along track, potentially by hundreds and thousands of kilometers along their orbit. That can make all the difference in a hit or a miss, for instance, if we're doing an impact hazard assessment. And so we have to keep track of these very tiny accelerations. Also, there's direct solar radiation pressure. The photons from the sun are hitting the asteroid. Marco has done some great work where they found that a number of asteroids were actually being pushed sort of off course, you could say, because of the direct radiation pressure, the photon pressure from the sun.
That's really interesting. It fascinates me that this is not and will never be a done deal. It will just constantly have to be looking and updating and understanding. In a sense, I suppose it's almost a bit like weather prediction. You can never say weather prediction is done. You're constantly looking. You're constantly reevaluating, and that brings me back to observations. So Marco, you said that you most observations are followed up by eye, so that you have a look. When you do that, are you, what tells you how close, say, an asteroid already is to Earth, and how do you calculate the positions of the asteroids on your images?
Okay, let's start with the first question. What tells me that an asteroid is close? It's not easy, actually. It's not something you see on first sight when you see an asteroid that moves through the stars. I mean, if you're lucky, you do. If the asteroid you see something that's moving particularly fast, then you know it's not actually intrinsic speed of the object, but it's actually just very, very close to you. So you see it moving fast. But that's it would be a mistake to believe that's the end of the story. Because as you can imagine, if you have an object that is very close to you, but instead of being flying in front of you, is actually coming straight at you, then, I mean, it will still move, but the motion will not be that much because you're only seeing the projection of the motion on the sky. So it might actually look pretty slow, and in the end being the most interesting one you found because it's actually heading towards you. So it's not something you can do straight away by just looking at an image. It's a more subtle process, and there's actually, again, there is mathematics behind it. We can talk a bit about that later. Second part of your question, that's a bit probably easier to understand. How do I do these measurements? This is actually, it's something that has evolved quite a lot in the last few years. The basic idea has always been the same. It's been the same for centuries. And it's basically, you have an image of the sky that has your asteroid, but also has stars. There are many stars. And stars, at least on short timescales, they're pretty much stationary. So you know where they are, you know the coordinates, the position of the stars. So what you do is you use the stars in your image to sort of get an idea of where you're seeing, what you're seeing in the sky, sort of map the coordinates in the sky onto your image by anchoring this map through the stars. And then now you see your asteroid, which is, you didn't know it was there, of course, but now that you have this frame of reference that has been established by the stars, you can measure the position of the asteroid in relative terms with respect to this reference system. And this is basically what we do. This is the astrometry we do. We use a catalog of known stars, which has billions of stars in it, to create this reference system, and then we measure where the asteroid is in our images. And the reason I mentioned this, that the fact that this is something that's still evolving and improving a lot, is because about now almost 6-7 years ago, there was a huge change for us. There was the fact that this space mission called Gaia, which is an ESA mission, a European Space Agency mission, that is dedicated to cataloging stars that are visible in our night sky, basically. It produced the first catalog of about 2 billion stars that we can see in the night sky to a level of accuracy that is much, much better than any other previous catalog of stars we had. So even something that is entirely on stars, it's a mission that observes stars, can have a huge, profound effect on what we do on asteroids, because now we can compute the position of asteroids much better because we are referring them to much better measurements of the nearby stars. And this is how a mission indirectly can help us dramatically. And it solved a lot of problems for us. Now we can do much, much better measurements of the position of an asteroid and much better predictions of the orbit of asteroids, thanks to this star mission that is Gaia, which is amazing for us. Yeah, that's basically how we do it.
Fascinating. Steve?
Yeah, I might just jump in, going back to that first question of how we know something might be close or not.
Also for you.
And this is probably maybe a good point to talk again about that dance back and forth between the observers and the orbit computing side. What typically happens is one of the major surveys. There's, say, 3 major surveys, Atlas, Pan-STARRS, and Catalina Sky Survey. They will find something that's not known and that looks like it might be a near-Earth object, but they don't do a detailed analysis. That they pass that off to the International Clearinghouse, which is the Minor Planet Center in Cambridge, Massachusetts. The Minor Planet Center will put it up on what's called a near-Earth objects confirmation page, because at that point, only one telescope has ever seen it. And it's probably not too much of a surprise that sometimes the telescopes will find things that aren't actually real, or that may be real but are artificial satellites in, say, around the Earth, not necessarily low, but even out as far as the moon and beyond. So they'll put this up on this page where other telescopes will go to that location on the sky, and they will get more measurements of that thing. Sometimes they may say, nah, we don't find anything there. And then the survey will go back to their images and say, yeah, maybe that was just an artifact in the images. That does happen. It's not frequent, but that's the point of this confirmation page. At the same time, when something goes on that confirmation page, here at JPL, we have a different monitoring system called Scout that takes those very few observations, and with different techniques, it tries to understand if there is any risk of an impending impact, say within a month. And if it finds any chance, then it notifies the same cadre of observers that this is something that's potentially here and now. We need more data on it. And so the key element of the observations will be, as Marco said, if it's going very fast, is probably close. If it's accelerating or decelerating on the sky, or curving on the sky, that's another indication that it's probably close. And so these are the cases that usually get raised early on. This is even before something has been formally confirmed or even formally discovered and announced as a discovery. We're already on the stick and trying to figure out whether or not this poses a threat to the Earth.
Yeah, exactly.
This is the sort of quick response system that I think that you set up there at JPL. Marco, as an observer, when you get something like that through, that there's the possibility of an impending impactor, what facilities can you call upon? How quickly can you get your follow-up observations? Sort of give me the sort of what happens on that day when you need to spring into action.
That's a very interesting process. And it's, as Steve said, fortunately now we have the systems in place that give us the alert within basically minutes of the time that an object has been reported, not even officially announced yet, just reported the preliminary data. And I get alerts on my phone. And what I do is in some cases, especially if there's something that can be really close, have to jump on it immediately. And immediately here really means minutes to a few hours. And this poses a very interesting problem that, of course, the Earth rotates in a day. So if I'm here in Europe and it's daytime and I get an alert saying, okay, you have to observe this thing in the next 2 hours, there's no way I can do it from Europe because it's daytime. So what do? We need to have access to a network of telescopes all over the world. And that's what we did at ESA. We basically got agreements with, I think, a couple dozen telescopes all over the world, different longitudes and different latitudes, both hemispheres, and basically literally on every continent, in order to be able to get this opportunity. So as soon as I see an alert like this, depending on the time of the day and where it is in the sky, I know that I may have a telescope somewhere on the planet that is perfectly located to observe it right at that time when I get the alert. And that could be anywhere. It could be in Korea, Japan, Namibia, Reunion, Australia, US, Chile, Hawaii, literally everywhere on the planet. And I need to have a telescope there. And we do have that. We have this wonderful network that we've set up, and we can react within minutes and get these observations in the spot where the asteroid should be. And of course, I mean, if we're lucky, we find it there. There may be cases, as Steve said, that was a false detection, a false alarm, and it was not actually an asteroid. But that's also very useful because not finding it tells us that it was not a real object, there was an artifact. So we have to do this, and we have to do this on timescales of hours and significantly less than a day for these objects that are coming towards us on very short timescales. And this is it's basically a parallel process to the one that we discussed before. So it also the orbit computation systems, as Steve said, are different because the second process happens on a time scale of hours. The other one happens on a time scale of days to weeks, sometimes years. So these two things go on in parallel with different systems and with different timescales. And also, for example, for us, with different instruments, with different telescopes, because it's one thing to observe something right now, and maybe if I need a telescope somewhere in the middle of the Indian Ocean, I'm not going to have the best possible telescope of the planet. I need to use smaller telescopes, whatever exists in that particular area of the planet. While maybe the other follow-up that we were talking before, that is more on long terms, allows me to plan ahead, a few days maybe, and schedule a telescope that is technologically maybe the most appropriate one. Even, I mean, I can let the Earth rotate until that telescope is in the right direction, because the time scale is more than a day. So this, again, these two different interplays are both happening in the community in parallel, and they require different reaction time, different technology, different expertise. Again, very interesting and very exciting when these alerts come, because it's something you have to do day or night, weekends, every single day, basically. Have to be there.
Yes, you're on call all the time. Steve, I'm just wondering, we've got a lot of the audience questions coming in, so I want to get onto those very quickly. But I'm just wondering, and Marco, I'll ask you the same question in a moment as well, but I'll start with Steve. You are both absolutely, you're world-class experts in this. You deal in these probabilities and of seeing these potential impactors and doing the maths, going through the process to get them off the risk list. You are cool customers by any measure, but has there ever been anything that you've seen that did give you a fright?
Well, I guess on the one hand, I would say yes, and I'll tell you about that in a moment, but probably we need to emphasize that asteroid impacts that are devastating to the Earth are things that happen on 100,000-year intervals or million-year intervals. And so you're much better to worry about whether you got your seatbelt on when you're driving your car than whether you're going to be taken out by an asteroid. This is why we're on the job. We're making sure that if there is anything coming, we're going to find out about it. And it shouldn't be too surprising. If we find something that is coming our way and it's potentially devastating, there is a lot we can do about it. And maybe that's for a different discussion, but we can push these things off course. So first of all, I want to make sure people aren't losing any sleep over that. On the other hand, we in 2008, I might tell a quick little story. We found an asteroid that was going to hit the Earth in 2008. It was October. I got a phone call from the Minor Planet Center saying, hey, I think this is maybe an impactor. Can you look at it? And I rushed to the office. I looked at it. And for the first time in my life outside of simulations, I saw the impact probability of 1.0000. And I'm like, that's startling. The very first thing I did was I rechecked the size of this object. As part of our calculation, we estimate how big it might be. And it was, say, 3 to 4 meters in size was what the estimate was. So I'm like, okay, well, that at least is nice. But the short moment between seeing the 100% impact probability and then seeing that it was verifying that it was a small size was a little, you sit up straight in your chair for something like that. That was the 2008 TC3 impactor that crashed into Sudan in 2008. And really precipitated, I think, in a real way, a lot of the effort that's been going on in the subsequent decades to get these rapid early warning systems in place, so we don't get caught off guard. And we managed to work through that in 2008, but we didn't have robust systems in place like we do now.
Marco, what about you?
Well, I guess the events are similar. I mean, the TC3 event in 2008 was, of course, it's an important one for everybody in this field. The only other time that, I mean, in a certain sense, we see some people could have been slightly worried was a few years earlier when what is now known as Apophis, one of the most famous asteroids was found. And Apophis, for a short time of a few days, had a 3-ish% probability of impact for a time that at the time was about 25 years in the future. So, and it's the kind of asteroid of about 300 meters in size that is at a level that can cause some pretty significant damage. So that was probably the only time where there was really a threat of something that could have been relevant for a fraction of this planet, not a devastating event, not something that takes out the planet, of course, but something that could have had pretty significant consequences on life on life on a specific tiny part of Earth where it would have hit. But fortunately, it lasted pretty short. It was just in about a week. We knew that it was not going to hit, and it was all clear. Then,
yeah, but
of course,
a lot of Christmases were ruined for that.
A lot of Christmas itself was ruined because it just happened to be to go across Christmas from the discovery to the all clear. Just Christmas was just in there, and it was a lot of fun. Then there were other cases where the excitement was more because we finally see that what we're doing actually works. And an example of this was in 2018 that we were not worried in that we was actually happy that it was working because we had the first completely functional alert out of the systems of a possible asteroid that was going to hit the Earth with almost 100% probability. Again, it was the same story, it was tiny, just 3-4 meters in size. But coincidence wanted that most of us were actually at the same place. Most of the community was at the same place because there was a conference going on in Germany. So we all kind of got the alert at the same time in the same point of like physically being together. And it was an exciting moment to see that what we've been working on really worked. We really got this prediction and we were really ready to react and get the observations. Then, of course, it was a negligible threat because it was a tiny object, but it's really exciting. It's probably one of the most exciting moments of my career was to see this happening with the coincidence that we were actually physically all together in the same spot. It was amazing.
Yeah, that was 2018 LA was the asteroid, and it hit over Botswana, northern Botswana, I think. And during the conference, it was quite a time.
Yeah, exactly.
I might, Stuart, you know, we've had 4 asteroids that have been discovered in space and then went on to hit the Earth. And it's a little curiosity, they were all 3 to 4 meters in size. And that's almost, it seems like a strange coincidence, but it's kind of an artifact of the way our system works and the way the solar system works, because larger asteroids, say 10 and 20 meters, they really don't hit very often, and you're not likely to see something like that on regular timescales of a few years. On the other hand, smaller asteroids, say a meter, aren't going to be discovered with our current telescopes until they're really too close to even trigger the alerting system and do anything about it, maybe just 5 or 6 or 8 hours before impact. But there's this sweet spot for 3 to 4 meter asteroids that get detected about 24 hours before impact. And 3 to 4 meter asteroids impact the Earth every few years. And so this is the size that we're seeing in our telescopes and coming through the system, and we're able to alert for these. If there were larger ones that were actually more threatening, like 50 meters, we would have weeks of warning with our current system, and everything would, you know, it's been tested on this 24-hour time scale. The weeks-long time scale would be very relaxed from our perspective to understand how to deal with that. Maybe for other folks involved in the crisis, it wouldn't be as relaxing, but compared to what we're used to, weeks is a lot of time.
Good. Yeah.
Absolutely fascinating to me. It's absolutely fascinating to me how fast this field appears to have evolved from a situation, say, 2 decades ago, where we're sort of really scratching our heads. So I was thinking, gosh, this is a problem. How do we deal with it? To hear you saying that, you know, we're in this sweet spot now where we can detect objects just a few meters across, you know, quite soon before they impact, but then those things don't do very much damage. It's extraordinary to me the amount of ingenuity and dedication and skill that people like yourselves have put into all of this. And on that note, we're going to turn to some audience questions now. So what I'm going to do is I will ask the question first to Marco, and then the next question I'll ask to Steve, and we'll alternate in that way. But if either of you want to jump in at any point and add to the question or add to the answer, then please do. So let's have a look at we've got a question here from Bruno Guillet, and he's asking about the object that would crash onto the moon on March the 4th. And he'd like to know, could that be an asteroid?
So should I be answering?
Yeah, go for it, Marco. We'll go for you first.
I mean, in most of these cases, the actual answer comes more from the dynamics than from the observations. The way we would observe an object like that is not that different from the way we would observe an actual real asteroid, but we do have ways to know, and basically two different types of ways to know. The more observational one is to study the color, the properties of the reflected light of the object, what we call spectroscopy, and see how it looks, and the color of the light, the way the different colors of light are reflected off the object, give us some indication of the material it's made of. And typically artificial objects look pretty different in this regard compared to natural ones. So this can be done, it has been done on that object, and it made it clear that it looks artificial, so it's clearly an artificial object. The second group of ways to do that is purely basically dynamical, mathematical, and it's also something that can be done on the basis of what we typically do, on the astrometry that we do, measurements of positions. And it's basically what we mentioned earlier, the fact that the motion of small objects is not purely gravitational, but it's affected by other effects, like what we mentioned, the solar radiation pressure, the Yarkovsky effects. These subtle effects are heavily dependent on the mass of the object and the density of the object. So something like an artificial object, especially if it's empty, is particularly light for its size. And these effects are particularly easy to see and detect on artificial objects. So by detecting these non-gravitational forces, these pushes caused by this phenomena, we can immediately know that this cannot be a rock, because it would not move like that. It would move with a less perturbation because it's heavier. So both these ways, these avenues have been used for this object, and they both, of course, agree that it is an artificial object, it's not a natural one. It doesn't mean that natural objects cannot be in similar orbits. There have been natural asteroids that have been captured in Earth orbit, in orbits that are not too dissimilar from the one of that object you mentioned, but that particular one, we know it's artificial. And the others that I just mentioned, we know they're natural because of the same reasons, the same checks.
I understand. Steve, I've got a question for you here from Mikhail Baskov. And he says, we hear sometimes about asteroids that were only noticed when they were flying by the Earth or even afterwards. So we didn't see them coming in towards us. And he wonders, does this happen often?
Yeah, it does actually. And so probably need to picture the solar system in your mind somehow to understand, but the telescopes we use to track asteroids can only point to the nighttime sky. In the daytime sky, about all you're going to be able to see is the moon, right? And so when an asteroid comes from inside the Earth's orbit and passes by Earth and going towards outside the Earth's orbit, we see it when it goes outside the Earth's orbit because it's going into the nighttime sky. So it's not at all unusual for us to see and discover an asteroid that just went by the Earth fairly close, and it goes into the nighttime sky. About half of the objects go the other way. They come from outside the Earth. We see them before the encounter, and then they go into the daytime sky, and you don't see them again after that. Now, you got to understand that when asteroids come very close to the Earth, most asteroids are tiny, right? There's very few very large asteroids, and there's a great many very small asteroids. And so most things that come close to the Earth are going to be quite small. And That's sort of for our good luck as humans, because we're more likely to get hit by these very small objects. And but our strategy is not necessarily just to do this short-term warning. We do that, but we're trying to get a catalog of the entire asteroid population down to a size that doesn't threaten the Earth anymore. That's going to take a long time. But then when you know all of the asteroids and you know where they're all going, then you don't have to worry about, oh, we just found one that came out of the daytime sky and flew right by us. That one will be cataloged, and it will be monitored through our impact monitoring systems, and it may or may not, find a place on the risk list. But we're watching and cataloging all of these asteroids that fly by.
And that's a huge amount of computing power that's going to need to sort of be predicting their future orbits. And that brings us to a question from Rosa Jesser. So over to you for this one, Marco. Could it be possible to predict asteroids' future orbits with the effects of flybys and everything with these quantum computers that we hear so much about? She wants to know.
Ooh, this is mostly on the computational side. So personally, I would not know what to say. I've never actually practically used any of these tools. I don't know if they're even available, even in an experimental way right now. Conceptually, I mean, here Steve would probably correct me if I'm wrong, but I think in itself, computing orbits of asteroids and probability of impact is not computationally that intense. I mean, humanity is doing things that are computationally much harder than this in terms of like computing resources, processing power. So probably it's not a field that's going to need very cutting edge computing technology. It's more the question of doing it, having the right data and having the smart algorithms and math to do things. That is what, of course, the Orbit computers do, than crude, pure processing power. If we had 1,000 supercomputers to throw at this, we wouldn't probably do any better at these predictions. It's just it's the math and the data that matters.
I agree, Marco. I think that that this is not computationally in terms of computer power, this is not that challenging of a problem. There's other challenges that we face. The storage data storage can be an issue, but still this compared to some of the other problems that are being handled every day in everyday world, like banking and online commerce, these are pretty small computational challenges. We have a small cluster that we use here at JPL. I think there's a small cluster at ESA. We're not talking about supercomputers for this problem. What we really need is more data, and telescopes, not computers, is the bottleneck for us in our work.
Understand. Now, gentlemen, we're rapidly coming up to our hour. If you could indulge me for a few minutes more, we're going to do what I like to think of as the rapid fire question and answer session to try and get a few more of these questions answered. Now, a couple of people, including Stephen Salmon and Mikhail again, have asked about mitigation missions, and you mentioned that there were things that we could do to deflect asteroids. So perhaps you could tell us just a little bit about what we might do to deflect an asteroid if one needs deflecting, and perhaps how those missions might be dictated by the amount of warning time that we have, for example.
Sure, I can touch on that. I mean, if this is rapid, then it's just a minute or so, but you could really dedicate a whole nother show to this topic alone. But there's a small handful of reasonable ways to deflect an asteroid. The easiest and most obvious is just to smash into it with a spacecraft, hit it with a hammer and knock it off course. That's not the most controlled approach, but it's the most straightforward. And we've done it before with Comet Temple 1 and the Deep Impact mission. And we're doing it again with the DART mission, which just launched a few months back and is going to hit the Didymos satellite Dimorphos in a few more months. So this is pretty straightforward. There are other more sophisticated ways where you get a lot more control, but those are really only very effective if you have a lot more time. And so there's these things like ion beams where you basically are hitting it and using the photon pressure or the gas pressure to deflect it off course. Gravity tractor is one that's talked about quite a lot. It's a very slow approach, but excellent control. So you can't do anything quickly with these slow push methods. Of course, if you have a very large asteroid and very little time, say less than a decade, you might be forced into some kind of a nuclear deflection technique, which has been quite well studied and is should be fairly feasible. So what I would say is, if there's an asteroid coming to the Earth, we have lots of ideas on how to deal with it, and I think it would not, in the end, hit the Earth.
Marco, do you have like a favorite method for deflecting asteroids?
No, not really a favorite method. The only thing that I think everybody who works in this field and wants to do this is a favorite time scale, and it's as early as you can. And that's the reason why people like what I do their job. It's basically, we need to know it as quickly as we can, because all these methods, whatever method you choose, is going to be way better and way easier if you can do it with 3 times as long time span before the possible impact. So yeah, that's the trick, and that's what I'm mostly working on. Get them early, because the earlier you get them, the easier it's going to be, any method you want to.
There's the old saying in this business: if it's your job to protect the Earth from asteroids, there's 3 things you have to remember. And the first is to find them early, and the other 2 don't matter very much.
Yeah.
Well, on that note, it feels as if that's a good place to stop. And so I want to thank you very much, Marco and Steve. It's been absolutely fascinating for me today, the clarity of your explanations and the way that you've brought this whole field to life. This is real, this is active. It's literally just something that you do, is to keep watching the skies, scanning for these asteroids, and, as you say, Steve, creating this map so that we can understand our solar system, the evolving asteroid population, and then whether there's anything that we need to do in the future to keep our planet safe. So thank you both very, very much indeed. We're indebted to you.
Thank you, Stuart.
Thank you all.
Thank you.
It's a pleasure. It's a pleasure. And thank you all for watching today as well. I'm sorry we didn't get through all of the questions today, but hopefully that you got a lot out of today. So we are Space Connexus, and we're associated with Asteroid Day, which will be happening this year on June the 30th. So keep watching. Every month in the lead up, we'll be doing events such as this. And again, all that remains for me to do is thank our speakers, thank you for watching, and wish you a very pleasant day or evening, depending on where you are on the planet.